Though we're specifically focusing on correlation during this chapter, I mentioned that correlation is one of our first inferential statistics. It's looking for a relationship between two variables in the case of correlation, but we're going to start talking about various techniques that can even look at additional variables. And really what makes them inferential is that they infer that the relationship that we find could be found in other populations. So what we find in our particular study or sample, or a researcher's particular study or sample, can infer to a broader group of people. So there's certain commonality with inferential statistics, and that's really what I wanted to talk about in this lecture, is just some of those common traits of all inferential statistics. So all inferential statistics include an actual test score. So you actually do calculate, regardless of what the actual statistical test is, an actual score. This is the actual calculation resulting in a value that represents how much the variance covaried divided by the total variance. So again, when we talked about correlation, we were talking about the fact that a correlation is the sum of products divided by the square root of the sum of squares x and the sum of squares y. Or, in simple terms, the amount of variance that covaries divided by all the variance in that variable. This is going to be the same for all inferential statistics. They may get very complex in their mathematical calculation. In other words, we may calculate it by hand or we may have a computer program calculate it, but all of them are going to be following this basic concept. Isolating the amount of covariance between two variables or more divided by the total variance in our actual study. So that's what we're actually calculating. And depending on how we calculate it, they may vary in the amounts that come out. So for example, correlation, or small r italicized, is going to range between 1.0 and negative 1.0. There are going to be other inferential statistics that don't follow this rule. That the test statistic may always be positive. The test statistic can actually be much larger than 1.0. But no matter what we're actually doing theoretically is we're always dividing the covariance, or in other words, the variables or variance that's related to each other, divided by the total variance in our sample. All inferential statistics are going to have a degrees of freedom, which is a conservative estimate of the sample size based on a mathematical concept. Each inferential statistic will have one or more degrees of freedom, and those degrees of freedom are a little bit of a leftover from when we actually had to hand calculate all statistics and hand look at tables to determine statistical significance. Anymore, they're more of a guide for our computers to let them know what they're doing, and it does give us some information on sample size, which allows us some idea for external validity. So for example, if I was looking at a correlation R, degrees of freedom 3, I would know that the size of that study was probably 5. If I saw an R, degrees of freedom 98, most likely that's 100 people in that study. So it allows sample size to be accounted for in estimating the probability of the relationship that is being due to chance, the random noise. For R, it's typically n minus 2. And as I said, it will actually even sometimes vary. And if you find a particular textbook that lists, for example, R of n minus 1, or you see that in an equation, simply use what's being presented. For the purpose of this class, we're going to treat R as n minus 2 in most cases. Once we actually have the obtained test statistic, we're going to look for statistical significance, which is an indicator of the probability of error. It doesn't tell us about how strong the relationship was. It doesn't tell us how meaningful the relationship does. It simply tells us what is the chance that we're wrong. And we're comparing the statistical test value, that which we calculated, to a minimum value based on the degrees of freedom, adjusted for the sample size. This basically creates a bar, and that bar is the alpha. In the social sciences, we've set that bar at 0.05, representing a 5% chance of being wrong. So the probability of error is the p-value. What is the estimated probability the relationship, when found, would be found by pure chance given the sample size? And that's kind of a complex concept, but that's really what we're looking at, is the relationship of how likely is it that we would find this just due to random chance. Because chance is random. You may have heard the concept that lightning only strikes once in the same space. That's actually incorrect. Lightning can strike multiple times in the same place. But what we do know is that when we try to plot where lightning strikes, outside of a few predictors, it's fairly random, which means that if we were actually looking at that across the board, we're actually going to find that sometimes it's due to error. There's a fair amount of medical studies, especially when we're looking at medical malfeasance, that, for example, has found a spike in a particular type of diagnosis, let's say a cancer, that is also correlated with a power line or a particular type of plant. Sometimes that is a meaningful relationship, but there is also the chance that we just had a spike in that particular illness that wasn't related at all. Um, I'm not saying we shouldn't investigate those things. I'm just saying that we should be aware that there's always the chance that something that looks like a relationship isn't. And that's one of the reasons that, again, science is based on multiple studies looking at things in multiple ways. And if we keep finding the same results, if study after study with a 5% chance of being wrong always finds an effect, that starts to mean we can be fairly confident that's actually what's happening. So for example, if I found a spike in a particular type of cancer next to our power plant, do I find that same spike in other places with other power plants? If the answer is yes, over and over again, every time I find a power plant that's recently been put in, I find a spike in that cancer, that starts to make a strong argument that we are actually finding an effect that's meaningful. However, if I find a statistically significant effect of an increase in cancer next to a new power plant, but we haven't ever found that before, we can't find that anywhere else, maybe something else is going on. It may actually just be a random spike. Chance is lumpy. Randomness is actually not as random. We tend to think of random as being randomly spread. And the larger the sample, the more likely it is. But there's also some lumpiness to it. Think about just rolling a dice from a particular board game, a six-sided die. You rarely are going to get a random sampling of 1, 2, 3, 4, 5, and 6 if you roll it 6 times. You're probably going to get more like 1, 3, 3, 3, 5, 6. There's a chance there. So we got 3 threes. Does that mean threes are more likely? Well, the next time we roll the dice 6 times, we might not get any threes. Again, chance tends to be lumpier than we think it's going to be. Once we actually know there is statistical significance, that's when we're going to calculate effect size. So we are going to present everything up to this point. We're going to present the actual calculated test statistic. We're going to present the degrees of freedom, and we're going to present whether it's statistically significant. If it is statistically significant, we're going to report an effect size as well. We typically do not report effect size if it isn't statistically significant, because when people see effect size, they assume that it was significant. We're basically saying not only did we find an effect, here it is. So we're going to be a little careful about when we present this. You should also always double check if a study is providing effect sizes, make sure they're significant before you really look at them. Generally, most researchers know not to present effect size if something isn't significant, but that doesn't mean that's always going to be the case in every study. Different effect sizes for most tests, but many are presented in terms of shared variance as a percent. For correlation, it's R squared. So again, generally speaking, when we look at effect sizes, most of them are going to be on a 0 to 1.0 scale, but not all of them. Some of them are going to have their own types of effect sizes, especially the more complex tests with their own bars as far as what is meaningful in difference. So again, for correlation, we've got these 4 things that we're going to see in all inferential tests. We're going to have a test statistic. For correlation, it's small r italicized. For a t-test, it's a small t. For a z-test, it's a capital Z. For an ANOVA, it is a capitalized F. So again, we're going to see different things. For the regression, it's going to be the Greek letter beta. We're going to have degrees of freedom. In the case of correlation, it's generally n minus 2. And each test is going to have its own degrees of freedom. And in some cases, for example, the ANOVA, we're going to have multiple degrees of freedom. We're going to have the statistical significance. The alpha is going to be set at 0.05. So what is the actual value of our test, the p? It may be presented as a less than if we're using old-fashioned charts, or the actual p-value if we're using a computer. Remember that if the p is less than 0.000, we're simply going to report it as less than 0.001. We never report a p-value of 0 because that means there's 0% chance of us being wrong. And there's always a chance. And finally, we're going to report effect size. And again, this is going to vary based on our inferential test. But in our case of correlation, it's going to be r squared. So r times by itself. And here we have an example of what we would actually see in an APA-style paper of how you'd present a correlation.